Hello, dear subscribers and watchers. Today is Codeforces Round 896, Div 1 and Div 2. Today will be kind of special recording because I will not make any tutorial, at least right away. So the contest lasts 2.5 hours, and after this time I have some plans. So the recording of the editorial, I guess, will be after the plans are finished. Still, you will get the recording of the participation, of course, and I will, as usual, explain my thoughts during the problem solving. So actually, even if there is no editorial at all from me, still I think it's kind of understandable from my interactive whiteboard problem solving what is the problem about and which ideas I used and which algorithms I apply and then implement. So I guess it still will be quite useful. Also, I have something prepared here. I have my team reference for ICPC. So there are several algorithms here which are pre-written. There are also a lot of algorithms which are not pre-written. So if we need, for example, segment tree, I will have to do it on my own. But if we need, for example, Gauss or Dinitz, then I can copy paste. Or FFT. FFT is very thoroughly tested in this repository. Suffix array kinda tested. There are several number theory algorithms. Like if you have a formal power series, I can take a cosine of it. No joke. Still, I don't think there will be problems on FFT. I think there will be some sort of dynamic programming, which are not easy to use pre-written code in. Maybe some strange data structures. It's kind of Chinese round after all. So you gotta be prepared. Okay, it's beginning. Let's go. Okay, it's not going fast. Okay, maybe we need M1. Ah, no. Okay, problem A. There is an empty matrix M of size n claims M. Jankawa examination is over. Some puzzle games. Fill matrix M using permutations of length M. Okay, we take maxes of all columns and maxes of these numbers. And we need to maximize it. Okay, so we have several permutations. And we need to maximize the maxes of these columns. So at least we want to make at least one column without zeros. At least one columns with zeros but no ones. With the zeros and ones but no twos, etc. How can we do it? Let's look at little numbers. For example, if m equals 1, it's easy to see that we need like a lot of zeros and a lot of ones, I guess. Okay, m equals 1, m equals 2 are easy. What about m equals 3? And we can see that we can get 3. But can we get... So, the answer is actually less than n, I guess. Hmm. Yeah, because you have n rows. And since you have n rows, the max in each row is at most n. Okay? The max in each row is at most n. Yes, so you have several numbers which are at most n, so the answer is at most n plus 1. The answer is at most n plus 1. Also, all the numbers in the rows are at most m minus 1. So also each max is at most m. So answer is at most m plus 1. So the answer is at most minimum of n plus 1 and m plus 1. Now let's tighten this up. So, for example, let's assume that n is less than m. Can we get n plus 1? Let's see in the samples. 2, 6. So maybe the answer is yes. So if n is less than m, we actually maybe can make n plus 1. But how? So it's like this. We need to get n plus 1. So the first column should be without zeros. The second column should be with 0 but without ones. The second one should be... Okay, so it looks like this maybe. And in this case, we actually get... So if here there are no... So it should be also no zeros here, no ones here, no twos here, no threes here. Okay, let's see. So let's assume that m is strictly greater than n. Again, so no zeros here, no ones. So I want to get n plus 1. So I need a column with all numbers from 0 to... Maybe let's make it like this. Okay, I need all numbers from 0 to n, actually. So here's no numbers n minus 1. Okay. I don't know. So, but we can actually use number like n, for example. Zero, 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 1, 1, 1. No, it's not nice. 0, 1, 2, 0, 0, 0, 0, 1, 1, 1, 2, 2, 3. So in this case, this is 4, this is 3, this is 2, this is 1, this is 0, if I do not have such numbers in these columns. I think it's feasible. I think it's feasible just because I like write it like this. Okay, so I just write the numbers like with diagonal layers constant. Okay, it's if m is greater than n. What if m actually equals n? In this case, I cannot do it because all columns will have max n. Yeah, so in this case, sorry. So in case when m equals n, I need to do something else. And also I need something for a case m less than n. If m equals n, I have a square matrix. And I think I cannot make there are so many tricky cases. For example, if m equals n equals 1, then the answer is 1. And when m is n is 2, then the answer is actually 2. Maybe it's always like n. What can I do for that? I think I can... For example, let's make for 6. Can it make... Or for 4. Okay, let's do it for 4. So here, no, 0, 1, 2, 3. Again, 0, 1, 2, 3. And I think what I want here is like this. Yeah, so here I have max 1, here I have max 2, here I have max 3, and here I have max 0. And so the answer is 4. Okay, so I just repeat one row twice, and then I do the same solution. And what about m is less than n? In this case, can I make like m plus 1? Let's again see in the samples. 4, 3 is 3. 1, 16 is 2. 6, 6, 6, 6. 2, 1 is actually 0. Always if m equals 1, it is 0. Always if m equals 1, it is 0. So it's tricky. It's tricky. So can I actually make answer m plus 1 here? I don't think so. Like I need no zeros here. For example, okay, m equals 1, it is always 0. If m equals 2, it's like always 2. Yeah, because I can fill one with 0 and the second one with 1s. Okay, if m equals 3, can I always make 3? And if n is greater? I think if n is greater, it doesn't matter. Yeah, because I just can repeat rows. Yeah, I can just repeat rows anytime I want. So actually the problem is now easier. So we read m and m. So after that we do the following. So before that, I need to print the answer, and the answer is if m equals 1, then it is 1. No, it is 0. And if it is not 1, then it is minimum of m and n plus 1, I think. Yes, so and after that, the only thing I need is to fill the array. So, okay, if n is greater than m, then I simply use diagonal rows. So for int e I equals 0, I equal less than n plus plus I. So vij equals difference between I and j and I modulo m. And otherwise, first of all, so here I say that vij equals also difference between jim, but not really. Here I need to put something like maximum of 0 and so here m is at least n. Like this, I think. I think something like this. Okay, let's see. I need several tests because these tests are trash. Okay. No, it's really bad. So actually it works if n is less than m. What's going on? So here I need minus n plus m. No, it's still not nice. I get it, yeah. No, it was actually correct. It was actually correct. Also, I need something like, okay, 6, 6 is fine. So here it is 3 because here we have 2, here we have 1, here we have 0. Here is 2. This is like, yes, it is 6, 0, 0, 0. Let me make some more tests. For example, I need 1, 1, 2, 1, 3, 1, 4, 1, and 1, 2, 1, 3, 1, 4. What about these? Like 11, yeah? So in this case, all zeros. Okay. 2, 1, 1, 2. It uses 2. Yes. Yeah, it makes sense. Okay, I need also, for example, 2, 2, 3, 3, and like 10, 3, and 3, 10. 2, 2. Yes. 3, 3. Yes. No, I want 4. Or even 5. I need 5. Yeah. I want to look at 5. So for 5, yes, it is correct. 1, 2, 3, 4, 0. So it is 5. Yeah. And here we actually have 6. Yeah, because of this is 5, this is 0. No. Ah, yes, yes, yes. So this is, for example, here we have 0, here we have 1, 2, 3, 4, 5, and 6. No, we do not have 6, we only have 5. Okay, this seems pretty reasonable. Let me recheck finally. This 3260. Yeah. 3260. Okay, we can submit it. Okay, we can submit it. Okay, we can actually submit it. I think it's source. It's not source 2. Yeah. Okay, let's see. Oof. It could be worse. It actually could be worse. We spent 19 minutes on this problem. So, John Howard examination. Everyone will come with some candies, and people at the party. Ith person has AI candies. They will swap their candies. To do this, they will line up in an arbitrary order, and everyone will do the following exactly once. Choose an integer p, non-negative x, and give his 2 to the x candies to the p person, and he cannot give candies to himself. So we need to make a permutation. So I don't get it. Can everyone just give one candy to somebody else? In the end, everyone should have the same. After all swaps, everyone should have the same number of candies. What about problem B2? What happens there? So we need to make a permutation. Let me remove it. We need to make a permutation of people, and everyone gives like the next person several candies. And the point is that the number should be equal in the end. What to do? So, first of all, we need to calculate the mean number. So actually, everyone needs to make some mean number, average. This is the goal. So after that, for each person, either he has already M candies and it's fine, or there is an issue, because like we have a difference, AI minus M. So delta I should be the difference of two powers of 2. Like, and actually it is, there is the only one way to do it, to express it as the difference. Yeah, if it is positive, actually, you can see there is only one way to do it. And if it is negative, also, only one way. Yeah, so for each power of 2, there are several people who need to get this power of 2, and several people who need to give this power of 2. So if at any moment this is not equal to this, then we hold, because it is impossible. So we assume that in every row there is same number of people. Actually, it works also. Okay, let's first of all solve it for permutation. Yeah, so if in any row it is not equal, then we halt. So otherwise, each person should give something to this person, and that's it. The problem is it's not always exactly possible. So we need to form several cycles, and in each cycle it should be always like non-negative number of candies for each person. For example, if we have several people with 2 candies, and each person should give 2 to the 10th candies to the next person, then it is impossible to perform such cycle. We need someone to start with, and after that we can complete the cycle. So is it always possible to start? I guess it should be possible to start. It should be possible to start. But why? Okay, we have some cycle. We have... It's actually... I don't know. So since it is a cycle, there is a number which is greater than m. Okay? But there also should be a number which is less than m. Or at most m. So this person gives something here. And if we're living in a sad world, then... Okay, let it be a, let it be b. Then we have that 2 to the power p is greater than a. And a is greater than m, and m is at least b. So actually, after that, b will become b plus 2 to the p. So it will be... Is it possible? And then he needs to give something back. So minus 2 to the q, it equals m. Okay. I don't get it. I don't get it. I really don't get it. What? So is it always possible? Maybe we need to look at the example. So again, the question is, we have several numbers, and the mean of these numbers is m. And each person should give like 2 to the p to the next person, and the next person gives 2 to the p2 to the next person, and in the end they all become equal to the mean number. The question is it possible to do it? To start from some place so that all numbers are non-negative at all times? And the answer should be yes, but I cannot prove it. Okay, maybe let's look at the minimum number, a2, and a1 gives something here, and then a2 gives something here. Yes, so it 2 to the p and 2 to the q. So a2 plus 2 to the p minus 2 to the q equals m. Since a2 is the minimum number, we clearly have that p is greater than q. And also there is some sort of 2 to the r, and a1 minus 2 to the p plus 2 to the q. I want it that a1 minus 2 to the p is at least a2 minus 1. Is it possible to prove? And this is like m minus 1 plus 2 to the q minus 2 to the p. Yes? Yes, so I wanted that a1 is at least m minus 1 plus 2 to the q. No, there is no way I can prove it because a1 can be very little. a1 can be very little. Sure. Okay, I think we can just leave it without proof because I intuitively I feel that it must be true. I intuitively feel that it must be true. So actually, if the numbers in all rows are the same, I think it is possible. Okay, maybe we can do it like this. So we have A, and we need to make it M. So A minus 2 to the P plus 2 to the Q is M. Then, and let's assume that A is greater than M. Then A minus M equals 2 to the P minus 2 to the Q. Yes, so A minus M is at least 2 to p minus 1. Oh no. Okay, again, maybe there is some number which is less than m. Then it gets something, and it gives something. So a plus 2 to the p minus 2 to the q is m. So p is at least q plus 1. So like a plus 2 to p minus 1 is at most m. Yeah, so there is some number a, and a plus 2 to the p minus 1 is at most m. So let's assume that the previous number is greater than m. B minus 2 to the p. Okay, let's like replace this. So this is at least b minus 2m and plus 2a. Okay, I can't see anything. So, okay, it is fine. It's fine that we cannot do it. Let's just try. Let us just try. Ah, and also there is a single number out there which should be just included in any cycle. It can be just included in any cycle because it gives something and it immediately gives takes something and it immediately gives it back. Let's try and do it. Actually, I believe it might be the answer. How do people do it? They don't even prove it. Okay, I think it might be okay to do it without the proof. So we read n. We also read v. Okay, let's do something like find dance. And here we print find ans b, and if yes, then yes, and otherwise no. Great. First of all, we need the sum of all numbers. And if sum is not divisible, okay, like let's do int r equals s divided by n, and if r times n is not s, then we return false immediately. Okay. After that, we need to register all numbers. Like, we need to register the powers of 2. Okay, so we like make vi y 30, I think. Maybe even 31. Let's do it safe. So we iterate over all numbers. I might want it to be m. So we have I minus m. We need to make it the difference of 2 powers of 2. Okay. So, okay, let's make it bool negative equals I less than 0. If negative, then I equals minus I. So if I equals 0, then continue. Then we need to say that it is the difference of 2 powers of 2. One of them is just count trailing zeros of I. Yeah. So after that we say I equals I plus equals 1 over little. And if after that I is equal to 0, then no, it cannot be 0. It really cannot be 0. So after that we say int big equals also built-in ctz of I, and I minus equals 1 over big. So if after that I, then return false. And after that, if nega, then plus plus y little and minus minus y big. Otherwise, the other way. And after that, we need all these numbers to be zeros. So if y I, then return false. Otherwise, return true. Let's check. I kind of feel terrible because I didn't prove this solution, and if I will be the only person who gets VA, it will be really sad. Yes, yes, no, yes, no, no. Let's try it. But I really do not want to have a VA. Okay. Seems reasonable. Problem B2? What about problem B2? It says the same thing, but let's check for VAs. Are there wrong answers? No, there are really no wrong answers, so we can just formulate a hypothesis and think it is true. Yeah, so standings is really mighty instrument, a mighty tool if you are working, if you're competing, because it can say you much about your hypothesis. So the same thing, but now we have several chains which might be unclosed. So what? In this case, so if actually the only thing which differs is if you have some number which is 2 to the I from the actual answer, it might be two different things. It might be really 2 to the I, or it might be minus 2 to the I and plus 2 to I plus first. So there are actually two ways it can be, two ways it can work. Yeah, so how can we solve it? How can we solve it? I think what we might need is we might need to go from top to bottom. We might need to go from top to bottom. Yes, let's try it. So we also store the information about how much we subtracted one and added one. Like sub 31 and add 31. Like this. Okay. So if big is equal to little plus 1, this means that we subtracted one time from big. And here, if big is little plus 1, then we added one time to big. So, and here we go from top to bottom, and we look at the numbers. So we look at yi. So if yi is greater than 0, then what we need to do? We need to undo several addings. Yes? Why yi is greater than 0? This is because here we have done some extra actions. So if yi is greater than added I, this means that we have a trouble and we return false. Otherwise, we can say that y. Now we undo all these things. So we say that yi minus first plus equals 2 times yi, and that's it. So okay, also if I then also return false. The same goes here. So if minus yi here is greater than add I, we kind of do the same thing. Yes, we kind of do the same thing. Let's try. Yes, yes, no, yes, no, yes. Again, no, but why no? Ah, here we should make sub. Yes, it seems reasonable. Still no. I don't get it. Why is it no? Let's look at it. Let's look at it. Yes, so let's look at several numbers. y0, y1, y2, y3, y4, y5, y6. Oh, this is because I needed one here. Okay, so we clearly have a problem. However, we also have, for example, sub 4, it should be at least 1, yes. I want I to be like 4. So here it is negative. It should be C. Yes. Let's try again. I think it can pass. Yes, it kind of passed. And now we look at problem C. During the summer vacation after Zhongguo examination, Tom and Daniel are planning to go traveling. There are n cities in their country from 1 to n. And the traffic is very special. Yeah, I and 2i and I and 2i plus 1. Making a travel plan, Daniel chooses some integer value between y and m for each city, which is ai. Let Si be the maximum value of cities in the simple path between cities I and j. The score of the travel plan is this. What kind of problem is that? Okay. Okay. So we have a like binary tree. Almost binary tree. The last layer may be not full. So we have a binary tree, and in each vertex we try all numbers from 1 to m, and we consider all paths so let's like make some summation. And so like we consider sum of plans. Let P be a plan. Okay, A is a plan. Sum for all A's. Sum from I from 1 to n. Sum of J from 1 to n. Maximum of AK, where K is between I and J, where the segment is like the path in the tree. So like if I is here and J is here, then we consider this path. So this is IJ. And we consider the maximum. So definitely we can rearrange it. So the only thing that is important here is the length of the path. So let's look from or L from like 0 to something like 2 log n. Okay, let length be the number of vertices. In this case, it's like starts with 1 and ends with something like this. Then we sum, then we consider the number of paths of length L and multiply it by sum of all A's maximum of AK, maximum actually of some L numbers. So sum of L from 1 to infinity NL times what? So here all numbers but this L are redundant. So the answer here will be m to n minus L. After that, what do we have? We like have one way to make the maximum 1, 2 to m minus 1 to m. No, L. I think L. So this number of ways to make it 1, this number of ways to make it 2, 3L minus 2 to the L to make it 3, etc. And something like m to the L minus m minus 1 to the L to make it m. So let's sum it up. For the last power, we will have m to L plus 1. And for these powers, we will have something like k to the power of L times L times k and minus k to the L times k plus 1. So actually just minus k to the L. So here we subtract all the numbers like m minus 1 to the L, m minus 2 to the L, m minus 3 to L, etc. And we finish with, here we have like 1 to the L, so minus 1 to the L as well. So this is like some constant, and all we need is find all these NLs. Yeah, actually, these things are independent. Yeah, so it's just sum of NL times like FL, where FL is this strange thing. Yes, this strange thing. Is M actually big? Yes, M is at most 10 to the 5. It is nice. It's nice that M is not big, because otherwise it would be miserable. M is not big. So we calculate all these numbers. So FL is easy to calculate. Let's just do it. And while we write, we will think. Yes, it's simply not that bad problem. Okay, so we read N and M. Is N 10 to the 18? Actually, N is huge. Actually, N is really huge. Fine. It's okay. So what do? We read N and M. Let's just calculate the answer for N and M. And find answer is something what we should do. The sum of M over all test cases does not exceed 10 to the 5. Okay, 10 to the 5th. So we kinda need all these powers. So like M plus 1 powers. So we make VI F, which is like M plus 1. And it is filled with ones. Then we do something. Actually, L should int M. N should belong long. So what is L? Might be like 100, I don't know, or 1000. So first of all, we need to multiply all these numbers by themselves. So for int I, int current F equals 0. So we say that for int I equals 0, I less than. Actually, I think we can start with M here and minus ones here. I think it will be great. So let's make it m minus 1 here, but also fm equals m. So first of all, we say that for f fi equals prod of fi and I modulo m, and current f equals sum of current f and fi. Great. Also, we have some sort of current uns, which we return. We say that uns is sum of uns and current uns modulo m. We also calculate NL. We say that current uns is prod of NL and current F modulo M. And that's it. So the last thing that we need to do is calculate NL. Let's think. So we have some sort of big tree, and we need to calculate the number of pairs of vertices with some distance. What we can do is actually calculate so the depth is at most like 60. So we can do in 60 to the third, iterate over all thirds of vertices. Like a vertex and some vertex in its left subtree and some vertex in its right subtree. And say how many ways are there to make such a triple. Okay. Okay, let's think about it. So we have some binary tree. And actually, yes, let's consider like these triples. Yeah, so we know the depth of one of these vertices, the other of these vertices, and the third of these vertices. So the distance is like k plus j minus 2i plus 1. The number of vertices on the path is this number. So let's consider the layer number I. There is some certain vertex such that here they are all still full of depth, of the maximum depth, and here it's like this, and after that it's still the full layer. So what then? I think put it like this, and we need to make vi and l. Fine. Let me just think. So if we have n vertices in our tree, then the maximum depth is like leading one of n. Yes, I think just leading 1 of n. Yes. Leading 1 of n, which is something like count leading zeros of n. And 63 minus it. Okay, so 63 minus built-in count leading zeros of n. This is D. Now, what is NL? Maximum number of vertices is, I guess, 2D plus 1. I think it is 2D plus 1. No, yes, it's 2D plus 1, but since we need the maximum number of vertices, we need 2D plus 2. Yeah, why? Because on the left part, it is D plus 1. On the right part, this is also D plus 1, but minus 1 because they intersect. So 2D plus 1. So NL is 2D plus 2. Then we iterate over. So D is the maximum depth, okay? D is the maximum depth, so we need to iterate at most D. Then we go from int j equals I, j is at most D, and we go through k equals I, k is at most D, plus plus k. Great. Simply great. So how many? And we need then to put NL. So int current NL equals something. And we say that NL of what? NL of k plus j minus 2i plus 1 equals sum of this number and current NL modulo m. So what is current NL? This is number of ways to choose 3 vertices on depth I and its children on depths k and j. So this is the maximum depth D. So if k and g are less than D, okay. Let me think. So if j is less than D and k is less than D, then what do? We just say that we can choose anything we want. We can choose anything we want. So we choose any ith vertex, and there are 2 to the ith such vertices. Then we choose any j vertex and in its subtree, in its left subtree. And this is like 2 to the maximum of 0 and j minus I minus 1. And 2 to the maximum 0 k minus I minus 1. Why maximum? Because if I equals j, for example, then we do not need to take minus 1. But if j is greater than I, we actually cannot choose any of 2 children of I. We, for j, need to go to the left, and for k, need to go to the right. So we need this strange formula. So we say int q equals like I plus maximum of 0 and j minus I minus 1 plus maximum of 0 and k minus 1 minus I minus 1. And we say that par and L equals power of 2 of u. And we need to pre-calculate powers of 2. I think we can do it for all numbers. For a lot of numbers, I mean. So static vi p, if p is empty, then p dot resize like c 1 here, and we go from I equals 1, I is less than c plus plus I. Pi is sum of pi minus 1 and pi minus 1 modulo m. And then we return pn. So this is power of 2 of u. Great. Otherwise, we need to think. Why we need to think? Because, for example, there are just problems. There are just problems. So let's assume that R is the last place where we have not full layer. R is the last place where we have non-full layer. How can we calculate it? It's actually pretty messy. So let's think. For example, we have 1, 2, 3, 4, 5, 6. So 3 is the last I equals 1. 3 is the last place. I think let's subtract. So let's subtract the power of 2. So we have 0. For example, for n equals 6, what do we have? We have 0, then 0, 1, then 0, 1, 2. And 3 we do not have. So in this case, 6 goes to 1. And 7 goes to 2. How can we calculate it? And for example, 5 goes to also 1, but 4 goes to 0. We can do it as follows. And also I think we need to calculate the number of vertices in this bottom layer. Oh, this is so sick. Are there counter tests for this? Yes, I think there are. So we need to take n minus 2 to the d, which is like, here is 0, 1, 2, 3. 0, 1, 1, 2. Okay, what about, we need to round something up. So we need to round up it to the number no, we do not need to round up anything. I think we need to take plus 1 here and divide it over 2 to the d minus I. Okay, let's check it for something else. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, for example, n equals 12. And I have I equals 1 and d equals 3. In this case, I need like 1. What do we have? We have like n minus 8 plus 1 over 4. And I need to go down, of course. So like n minus 7 over 4. Let's check it. So if I have 11, then I subtract 7, it gets 4, then I divide by 4, I get 1. So 1. If I take... Yes, I think it is okay. Let's now put it here. LLR equals... So n minus 2 to the d plus 1 over d minus I. Yes, this is R. This is the number of vertices which are totally fine. Yeah, so we have R vertices which are fine, then one vertex where there are problems, and then again, like 2 to the ith minus 1 minus r, where there is everything fine, but there are only d minus 1 instead of d. Okay. Let's calculate answer in this case. So there are 3 addends. So the first addend is simply... It's really simple. It's just... It's the same thing as here. But instead of I need R. So I say car and L is prod of 2 things. R modulo M and power of 2 of U. Modulo M. And then I need to add one addend for this one. What do we have here? We have just one tree. And we have 2 subtrees here. So first of all, we need to find out how many Ds we have here. And this should be easy. This kinda should be easy because, like, we need to take n. First of all, we need to subtract all these top vertices. So like n minus 2 to the power of d minus 1. So first of all, we subtract it. We get the total number of bottom numbers. And then we need to also subtract r times 2 to d minus I. Okay, this is really doable. This is really doable. So first of all, we need long bottom equals n minus 1, n actually plus 1. Then we need to subtract 2 to the d Then we need to subtract r to d minus I. Yes. This is what we need to subtract. This problem is a real mess. Okay, we need to subtract it, and after that, we get the number of vertices here. Also, if I equals okay, let me make some other case. And I need one more case, which is if I equals d. Why? Because it is much easier. I just need to take LL bottom, which is this. And actually car NL is as simple as bottom modulo M. Okay. So what do I do here? I need to add the answer for this strange tree. So here I take J and here I take K. Let's do it. Let's do it. So let's make like int strange equals strange, and then I say that car and L equals sum of car and L and strange modulo M. What is strange? We need to multiply the answer for the left part and for the right part. So for the left part, if J equals D, then okay, first of all, if J is less than D, I take it as usual. I need to take strange equals power of 2 of this maximum. Otherwise, I need to calculate strange some other way. And the same thing goes for K. So if K is less than D, I need to make this. But here I need to say that it is product of strange and this power of 2 modulo M. And otherwise I need something else. Okay, what is the answer here? Here I say that this is just the number of vertices in this half. So what is the total possible number of vertices in this half? It is 2 to d minus I minus 1. Yeah, so here I say that it is some minimum modulo M. Minimum of what? Minimum of 1 LL to d minus I minus 1. Or bottom. And here I say, actually to debug it easier, let's do this. Yes, so here I say the strange is product of strange 1, strange 2 modulo M. And here I say this. And here I say this. So what do I do here? So it's either bottom minus this, It's maximum of 0 and bottom minus this. Okay, it's kinda ready. Let's see what it says. I think the answer will be incorrect, because it's always incorrect in such problems. Stop. Why? What is L? I do not need L. So, actually L is 2 times d plus 2. This is the maximum possible length plus 1. And here we need to say that it is less than L. Okay, 6, 13. Okay, it's already incorrect. But we can actually find this out, because it's not that bad. Yeah, so the 3 to 2 is really easy one. So let's investigate it. I think I will need... Let's just make 2 arrays, okay? NL and F, actually. So here I just say that FL equals sum of FL and something else. Oh no. Let's be NF. Stop. What did I do? Ah! I kinda messed up. No, I didn't mess up. Everything's just fine. So here I do this product thing. And then I say that NFL is sum of NFL and Fi modulo M. Great. And in this part, instead of doing all this stuff, I say that car F equals just NFL. Okay. And I need to find answer for 2, 2. This is more than possible. So, first of all, we have D equals, it should be 1, and L should be 2. 3, it should be. Why L is 4? Okay, 4. It's fine. After that, we need to look at NF and NL. So what it says that there are 2 paths of length 2 and only 1 path of length 1. And this is terrible. Actually I need to double all paths which are not the same vertex. So if the path is not the same vertex, I need to double it. Yes, I need to double it. Fine. I kinda messed up. So here I say that if I is not equal k or j, or I is not equal j, Then I need to do it again. Here we go, but no. Now it's 20. Why is it 20? So now NL is fine, but this is not. For example, it says that if I have like 3, in the end I actually need to multiply it by something, by m to the n minus l power. Okay, let me do it. I think let me do it. So int pm is an array of size of which size? No, 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 not of size n, of course. Instead, I will need to make some binary exponentiation, I think. Yes, it's not nice. It's not nice. So here, int ardent equals okay. So here, I think car ff equals prod of current f and something else modulo m. So here I need to it's a pity that I do not have a power mod with long. Let's add then. Okay. So here we have long, and actually the same goes here. I think I can just write int answer equals 1 while b, if b and 1 ans equals prod ans are b, and if b is divided by 2, then a is prod of a b. And then in the end, return ans. This is power mod with long. Here I apply this version in which I use like m n minus l modulo m. What's wrong now? Why is b minus 1? Actually, n is greater than l. Okay, it should be less than minimum of L and n minus 1 and plus 1. So now it's still 20. Let's investigate. So the answer should be 19, not 20. So there are definitely two paths which are in the same vertex, and the answer should be 6. Why 6? Let's see. M equals 2. So there is one way to choose answer 1, and there are 3 ways to choose answer 2. No, why 3? There are 1 way to choose answer 2, and this is all multiplied by 2. So yes, this is definitely 6. So why is it 19? Why is it 19? Ah, j equals I from I to n. So actually I was correct here when I didn't do it, because I considered only different paths. So again, we get something like 13? Why 13? Why not 19? Again, let's see. So we have two paths of length 1. And they give total of 6. And also there is one path of length 2. Yes, there is one path of length 2. And it can give either 1 or 2 or 2 or 2. So yes, it's kind of 7. What's wrong then? What's wrong? Why is it 19? So actually 6 should be doubled. But why 6 should be doubled? Why should 6 be doubled? So again, what's the point? First of all, I have two paths of length 1. Secondly, in each of these paths, I choose one vertex as a path, and the second one can be arbitrary. And finally, for this, I iterate. Yes, so actually, NF should be 6, not 3. Why NF is 3? Ah, sorry. It should be car FF here. Of course it should be car FF here. Now it's, of course, 19. Yes, now we remove this, and maybe we luckily get the final answer. Yes, it's kinda legit. Yes. Problem D. Are we sure we can do it? We kinda believe we can do it. A pseudo-tree is a connected graph which has exactly one cycle and no self-loops. It can contain multiple edges. It is a very difficult proof. I do not recommend anyone to deep into details, because you will sink into these details and drown. After deleting all edges on the cycle in a pseudo-tree, a forest will be formed. It can be shown that each tree in the forest will contain exactly one vertex which is on cycle before removing the edges. If all trees in the forest have the same depth, when picking the vertex on the cycle as a root, we can call the original pseudo-tree flower-like. Our friend has a flower-like pseudo-tree with n vertices and n edges. However, he forgot all the edges in the pseudo-tree. Fortunately, he still remembers the degrees of the vertices. Every problem is solved. Are they nuts? Or are the problems actually solvable? Nobody in top 20 solved E or F. So E of F. What are with these guys? Why they solved these problems? What the hell? What? So like I zone. What did he solve at all? He solved only F. No, this is crazy. We are not doing that. We are not doing that. We just solved D and we are happy. We just solved D and we are happy. He forgot all the edges in the pseudo-tree. Fortunately, he still remembers the degrees of the vertices. Specifically, the degree of the ith vertex is di. You have to help construct a possible flower-like pseudo-tree with n vertices, where the degree of the ith vertex is exactly di. I'll tell him or tell him that it is impossible. So again, we know the degrees of all vertices. We know the degrees of all vertices. We need to construct a flower-like graph or tell that it is impossible. I think it shouldn't be that bad. For example, why is it no? Okay, for example, second one. 1, 2, 3, 4. Actually, what I want to do is always make a pair of multiple edges and then do something. Why is that? That is because otherwise it's kinda hard. It's kinda hard to do it. So I will have at least 3 different trees, and I also need to keep track of their depths, and this is kinda hilarious. So assume that I chose a pair of vertices, which will be multiple vertices with multiple edges. Then I can just remove these 2 edges, and now I just need to divide all other vertices between these 2 trees. I need to form 2 trees with the same depth. How can I do it? Actually, I don't see any trouble with it. Yeah, for example, assume that we have 2 trees of different depth. Here and here. What's wrong with it? So assume that this depth is lower than this depth. Okay, so I have a tree with low depth and a tree with high depth. So first of all, let's assume that the delta is at least 2. In this case, I'm sure it is impossible. Why? Because let's take some leaf from here, some leaf hue. And let's take any vertex of here, and it has a parent here, and it has a parent here. It actually has several, maybe, children. So what I need to do is swap y, u, and w. I need to swap u and w. Actually, I can always do it. Why can't I always do it? I just need to swap u and w. The problem is maybe the depth is subtracted 2. Subtracted 1 here. Yeah, so maybe v and etc. were the only vertices on the lowest level. But if delta is at least 2, I can always do this procedure. Also, I kinda cannot do it when degree of u is 2. Yeah, because it's impossible. But in this case, it was just a bad idea to put it into a cycle. Yeah. Actually, if all numbers are 2s, then I cannot do any better than make a cycle of them. And this is the only thing that is possible to do. But otherwise, I don't think so. Actually, there might be several cases. For example, if there are all 2s, then this is the proper way to do it. But if there is like several 2s, only one number which is greater than 2, and maybe several 1s. But if we have several 1s, then I think it is already possible. No. No, it is not. So if we have several 2s, and something greater than 2, and several 1s, then I think we have a trouble, because I need to pair up some vertex of these with some vertex of these, they will have like a cycle, maybe a greater than 2, but still there will be vertices with 0 depth and with non-zero depth. This is a problem. So in this case, it is actually impossible. 2s and several 1s is impossible because of the sum of their degrees. What are we left with? So the case is there are at least 2 vertices which are at least 3. There are at least 2 such vertices, and in this case I can pair them up. So the question is this a criterion? I think no, because here we have the answer no, but we have several vertices of degrees 2, greater than 2. So now we have the following problem. We have made a cycle, but we have 2 trees which differ at 1. Yeah, so there are 2 trees which differ at 1. Oh, not like this. So the depth of this tree is at least is 1 plus depth of this tree. So if there are at least 2 vertices on this level with children, then it is fine. I can make a swap as I did before. The problem is sometimes I do not have several such vertices. What can I do then? The other thing is I can swap it with some inner leaf. I can swap it with some inner leaf. Also, sometimes I can swap it with itself. Yeah, for example, if I have a leaf on the level L and a leaf on level L small, what can I do then? Let's assume that they have some common ancestor. Then I kinda can swap. What? Oh no, the other way. I just can take. So let's do the following. Let's consider this leaf. Let's consider this path, and there are several maybe leaves here. What if there is at least one more non-leaf vertex? In this case, I have a lowest leaf there, and it has some vertex here, which is not in this path. And in this case, I can put this leaf here and put this vertex here, and actually increase the depth by 1. So the only possible way is I have a long path long path with only leaves. And the same goes for this tree, or otherwise, again, I could take some other such vertex and do this trick. So can I reduce the depth of this tree by 1? Maybe. It should be possible with some kind of operations like put this vertex somewhere here. It should be possible. So the problem is I have two trees which look like this. A long path with some pines here. I don't know. With some needles, I mean. So why can't I really decrease some of the depths by 1? Why can't I do it? So assume that I have... Okay, so I have some root vertex. And I have some other vertex here. And assume that I have one more vertex here. Then definitely I can swap this and this. So if I have depth at least 3, it is possible to decrease it. Surely it is possible to decrease it. Depth is at least 3. Ah, no. Maybe there are no children here. Yeah, maybe there are no children here. So what then if there are no children? So now the tree looks like this. It is a path. And here no leaves. Here no leaves, here no leaves, here no leaves. And maybe here there might be some leaves. But here, for example, no leaves. So no leaves here. So actually there are only 2 vertices which might have leaves. So 2 vertices with leaves. What does that mean? That means that we have a lot of vertices. So first of all, degree of root is 1. Or not. Is the degree of root 1? Okay, maybe. Okay, just let's subtract 1 from each degree. So now we have the number of children for each vertex. And it seems that we have the following. We have at most 1 vertex, at most 2 vertices with at least 2 children here, and at most 2 here. What happens if we have at most 2 vertices with 2 children? It means that we have no branching, and we have to make one of these vertices the son of the other one. Do we need to make an example? Ah, yes, we also need to make an example. Oh. This is actually a possible problem, but it's a huge pain. So first of all, we need to choose 2 vertices. Okay, let's start to write this problem. Although, actually, it's a bit ugly. So number of test cases. Number of vertices, then we say we have vid of n, we read d, then we say find ans of d. Then if ans.empty without no, otherwise without yes, and we print all the edges. Yes. And here we need to find ans. PPII of VID. Great. So there are several cases. So first of all, I need to find the sum of degrees. Sum of degrees plus equals I. Yeah, so if after that the sum of degrees also const int n equals d dot size. So if the sum of degree is not n times 2, then there is an issue. Yeah, and we just a moment. Oh, great. So if it is not n times 2, then we need to return nothing. What next? So now we need to find... So let's find the min element of D. And if it is 2, then we just need to make a Hamiltonian cycle. So we say E of n. Actually, yeah, we say that EI dot x equals I. Actually, just EI equals I and sum I1n and return E. So now we have some leaves, some maybe vertices of degree 2, some vertices of degree greater than 2. then what do we try to do? So the issue is when we have two vertices like at most two here and at most two here. And this is an issue. So all these vertices should be at least two, at least three even. Now, so we subtract 2 from them, and from everything else we subtract 1. Let's make something like a pool of all leaves. So if di equals 1, then leaves dot pushback of I. Yes. What then? So what are some bad configurations? For example, 3, 3, 3, and 4. It might be bad. No, actually, if here there are exactly two vertices with branching, and here there are exactly two vertices with branching, then everything is kind of fine. No. Okay, assume that we have at most two vertices with degree at least 2. Then assume that the total number of vertices which are not leaves is like L. Actually, can't we make a branching? So maybe assume that we have like 4 vertices with branching. Yeah, so 2 here. And 2 here. In this case, we kinda can put this either here or here. So the answer is also possible if we have 4 vertices with branching. And how can we get that? We can get that how can we get that? I'm not fast enough to do it. Sorry, guys. I'm just not fast enough to do it. So we have vertices 4. Like, again, let's assume that we have subtracted 1 in the beginning, actually. We have subtracted 1 in the beginning. Yeah, so like we do this. And we just do that for int I from D minus I. Sum of degree should be now n. Yes. Now it should be 1. Now it should be 0. So the vertex with branching is a vertex which is at least 2. So there are also vertices which have 1 actually. So there are several zeros, there are several 1s, there are several 2s, there are several 3s, and there are several at least 4s. So the vertex which is at least 4 is universal because it can even be a root, because it just no, even 3 is universal because it can be even a root. So it's totally fine to be a root. So if I have at least 2 times 3 and at least 4 times at least 2, then it's totally fine. Let me just VPI like vertices of degrees 4. So if di is less than v dot size, then vdi dot pushback I. Else v dot back dot pushback I. Okay, we constructed it. Let's then make some easy things. So now both things are zeros. So each vertex. Okay, there are some simple cases actually. There are some very simple cases. When for example, when let me think. Oh no, 9 minutes. So if v second dot size plus v third dot size is at most 1, then I return empty, definitely, because it is impossible. Now actually I know the total depth. The total depth is something like total numbers of 1s, 2s, and 3s. So if it is even, it is also really easy. Why? Because make two roots. Root 1 is I make 2s and 3s in a set. Now I say that I have this. I say that int root 1 equals root v230 r2 equals v231. So vpii e. So I say e dot in place back of r1 and r2 and again. And after that I do some strange things. Now I make a counter for leaves. And I do this thing. Here I say that I need to work with vertex number, actually the current vertex. So first of all, I say that it should have this number of children. Yeah, so I say that e dot in place back. What? I should connect car1 with v0 c and t plus plus. Okay. Now if I equals depth -1, I do it again. However, otherwise I need to find a new vertex. So while v1 to 3 cnt equals r1 or v1 to 3 cnt equals r2, need to make cnt plus plus. After that, I say that e.eb of car1 and this, this, new car, and car1 equals new car. And the same goes for the second one. And here should be not CNT, but CNT1 to 3. Okay, I really tried, but it's not worth it. So conceptually, what do we do then? So if it is odd, then it's still usually possible if it is big enough. Yeah, so we have leaves, which are zeros, 0 children, 1s, 2s, and 3s. So if v3 is at least 2 and v2 plus v3 is at least 4, it means that we have a branching and we can make a replacement. But it's so hard. So hard. So, and here I return E. In some other cases, okay, let's just see what kind of place I have. '82nd place. This is not really bad, but it's definitely not a nice participation. People who solve D, they actually get 17th place. 20th place. Okay, there are like 26 people who solved anything besides ABC. Or Turmax. He didn't solve problem D for some strange reason. D is definitely a solvable problem, but as I said, it is messy to write because there are a lot of cases. So kinda in this case, we need to put 2 vertices of degree 3 here. Yeah, so now they are branching. After that, we need to put 2 vertices of big degree here and here. And then we need to proceed with some chains. And this is also not always possible. Or is it? I think it is possible, always, yeah, because yeah, there are 4 vertices, but also it should be at least 5. Yeah, because the total depth should be even. It should be odd, yeah, it should be odd, or else we have already won. So actually, at least here we can put one other vertex, and we are totally fine. And if there is a variable depth you see here, yeah, so it should be depth -1 in both cases. So it is in this case. There are also some other cases, like v3 is 0, v3 is 1, and v2 plus v3 is at most like 3 or 2 or 1 or 0. They all can be considered, but it's messy. Okay, I think I think the deep observations will be in several hours. So thank you for watching.